Hello, this is Team 12, and today we are presenting the Unmanned Aerial Ground Vehicle, a remote-controlled flying and driving robot. The Unmanned Aerial Ground Vehicle, or UAGV for short, was created to aid visual mapping and search and rescue missions that happen beyond visual line of sight. Some existing products used for visual mapping and hazard detection are the DJI Matrice line of industrial application drones and the FLIR Unmanned Ground Vehicle. A popular drone from this line is the 200 series, which has a large lifting capacity and a maximum flight time of 13 minutes with a 2.4 kilogram payload. The FLIR First Look vehicle, on the other hand, is marketed as a rugged, throwable robot intended for surveying hazardous situations. While these vehicles seem promising, both lack the full maneuverability of having both flying and driving capabilities, which might be necessary for these applications. For example, in order to scout a location, the first look is intended to be thrown through an opening and remote controlled, but has no way of maneuvering across obstacles it encounters. The large frame of the DJI drone limits the visual surveying to a broader scope, as the flying maneuverability in and around obstacles such as buildings is very difficult. The only vehicle that was found to fly and drive available on the market was a ground-air drone toy, with a maximum flight time of 8 to 12 minutes in flying mode and no additional payload. The goal of the UAGV was to create a highly maneuverable vehicle that can switch between ground and flying modes when one or the other is preferable due to terrain or weather conditions. The applications are not limited to this scope, with a swappable payload of up to 300 grams that can carry an emergency relief package or special thermal imaging camera, to name a few examples. Let's take a deeper look at the different functional systems that make up the UAGV. The mechanical systems of our UAGV consist of a steering assembly, rear-wheel drive gearbox, suspension system, payload distribution, and chassis. Let's start by looking at the chassis design. We decided on dividing the chassis into two separate levels. The bottom level can accommodate a payload box that contains crucial supplies such as food, water, and first aid for search and rescue operation. The bottom level also houses ground systems, such as steering and drive motors. The upper level is an isolated section, meant for sensitive and critical electronic components. Now onto the steering. The steering system is an independent two-servo tie rod design that takes up the least amount of space while also ensuring a turning angle of at least 30 degrees. The steering system consists of three supporting bars. The top two are the tie rods, responsible for turning the wheel, while the third bar is the load-supporting control arm. The rods are integrated into the wheel hub, which isolates the wheel's rotational motion from the linear contraction of the tie rods. Moving on to driving, the UAGV uses a rear-wheel drive to propel itself while on the ground. It features a simple power transmission design that uses two gears to transmit power from the motor to the axle. The last component of the UAGV's ground travel is suspension. Instead of creating a new subassembly devoted to suspension, our UAGV has TPU 3D printed wheels, which incorporate suspension directly into them. This lightweight 3D printed wheel has a compressing honeycomb design, which allows the UAGV to traverse over rough terrain while maintaining a relatively horizontal chassis angle. Let's now take a look at the electrical systems that allows for communication and propulsion of the vehicle. The UAGV features a live first-person view video feed, global positioning system, and onboard sensor suite that allows the operator to view the status of the vehicle in relation to its surroundings in an intuitive way. The operator can then use the remote controller to maneuver in either ground or flight mode, which sends signals to the Pixhawk Mini computer on the UAGV. The Pixhawk Mini calculates values to send to all the motors connected to the computer, adjusted for inertial sensor data provided by the redundant measurement units inside the Pixhawk Mini computer. In order to be useful in application, the UAGV needed to have an overall mission time of at least 20 minutes. We used eCalc to verify our flight results in standard atmospheric conditions. The UAGV's flight motor configuration allows for a hover flight time of 5 minutes and a thrust-to-weight ratio of 1.8, which provides smooth control characteristics. When optimized for range, the UAGV can fly up to 2,270 meters and go as fast as 100 kilometers per hour. For our drive system, to ensure our vehicle is able to traverse across a wide range of harsh environmental conditions, we can demonstrate the simulated performance of our drive system using a MATLAB simulation. The simulation calculates the total motor tractive effort required for the vehicle to propel based on our design constraints. Environmental conditions such as ground rolling resistance and incline resistance were taken into account in the simulation. The simulation also considers the maximum load the motor is capable of producing before it operates above the current limit specified by the motor manufacturer. Here we simulated the performance of our selected drive motor at angles of inclines ranging from 0 degrees to our maximum grade requirement of 30 degrees. For each iteration of our simulation, we considered the worst possible surface friction condition we expect our vehicle to traverse in. In all cases, the drive system was able to propel the vehicle at a rate of 1.5 meters per second squared within 2 seconds. With a 4S LiPo battery, our selected drive system can achieve an overall drive duration of 20 minutes at an average speed of 3 meters per second. Despite the added weight of the flight system, this performance is on par with many RC crawler vehicles available in the market. The system is also capable of driving across surfaces such as concrete, dirt, asphalt, and sand. The firmware running on the onboard computer is based off of ArduPilot, an open-source software for unmanned vehicles. Every vehicle comes with various manual and autonomous modes. Our objective was to put together a cohesive firmware that was able to utilize both ArduPilot's ground and aerial capabilities. Software in the Loop, also known as SITL, is a simulator that allows one to run ArduPilot code on their computer instead of a flight controller. We will use this to demonstrate the workings of the firmware. We went through many different methods of combining the vehicle archetypes. Eventually, we decided to create a flight mode within Copter called Drive Mode that utilizes only the ground motors and allows the user to drive the vehicle manually as a rover. Firstly, let's take a look at Rover, which Drive Mode was based off of. When we run SITL, we can demonstrate rover inputs and outputs through these Mavlink instructions. To begin, we will simulate arming the motors. This is a safety precaution to prevent any unintended motor movement. Then, using an RC instruction, we can simulate remote control. Throttle is set to channel 3 by default. We can see the rover moving forward now. Typically, for an aerial vehicle, channels 1, 2, and 4 are for roll, pitch, and yaw, respectively. However, channel 1 is used for steering inputs in the rover vehicle type. In our drive mode, we are also using the roll channel to control our steering. To utilize drive mode, we need to switch over to the Copter vehicle type, which is shown here as mode 27. When we change the RC inputs, the outputs will change as well. Our drive mode incorporates a servo steering system. High logic signals sent for 1000 microseconds, 1500 microseconds, and 2000 microseconds are associated with 0 degrees, 90 degrees, and 180 degrees respectively. Finally, we can take a look at Copter's autonomous flight modes. Keep in mind, although we are only demonstrating the automatic flight modes, Copter does have manual flight capabilities as well. We can draw missions by giving the UAGV GPS coordinates. As well, at any given time, we can locate and manually log the UAGV's location. With a home coordinate set, we can make the UAGV return to the landing zone. After a couple of months, we completed much of what we set out to do with our UAGV despite the restrictions. It was capable of transitioning between flying as a copter and driving as a rover, and able to carry a small payload to a desired destination. But there were more features we wanted to include but did not implement as of yet. An improvement we plan to make is to have our payload delivery system be able to remotely unload our supply package while in flight. We also hope to be able to build and test a physical prototype when safe to do so, and continue further on with the project. At the end of the day, we built the UAGV because of its meaningful applications, and we hope that it can bring help to those who need it.